Chapter 29 is all about magnetic forces and fields. And this is a very long chapter, so we need to settle in for the long haul. In studying magnetic forces and fields, we want to look at a magnet and understand what it is. We've seen magnets before, and one of the most popular types of magnets that you'll see out and about is something called a bar magnet. It looks like a bar, and it has two ends. It has a north pole and a south pole. And every magnet actually has these two poles, no matter what. I could cut this magnet in half. If I cut this magnet in half, and I separate it out, pull the two halves apart from each other, they actually set themselves up so that there's still a south pole over here, there's a north pole on the right-hand side, but they induce a north pole and a south pole. So you cannot cut two poles apart. You cannot cut apart two magnet poles. Every single magnet has two poles. This means that there is something called no magnetic monopoles. For extra credit, if anybody can go out and find a magnetic monopole, I'll give you some extra points. And we've seen this with magnets before. If you've actually taken two magnets and held them together, they can attract each other. And it turns out that opposite poles of a magnet attract, much like electrical charges. Opposites attract, and like poles actually repel. So two norths will repel each other, two souths will repel each other, a north and a south will attract each other. And this recognition suggests that there's something similar between magnetics and electronics. Magnets and specifically magnetic poles seem to act like electric charges. And this will turn out to be a very big deal and very useful. This became very, very useful and very interesting for people in the 19th century, in particular a physicist by the name of Michael Faraday, who was studying magnets and electricity. And what he noticed was magnetic forces, magnets, could induce electricity. He could make current flow inside of a wire by holding a magnet towards it. They also noticed that electricity could induce magnets. So magnetic things are electric, and electric things are magnetic. This led to the discovery of something called the magnetic force. Which actually originates from charges in motion. So moving charges, also known as current, are responsible for the magnetic force. We're going to work on understanding this magnetic force, and we're going to work on understanding this through something called the magnetic field. B represents the magnetic field. In your textbook, they talk about the magnetic force in section 29.1. You're welcome to read this, but I think it's a little bit confusing, so I'm kind of going to skip over section 29.1. And we'll talk about the magnetic force as we go through and talk about the field. So let's look at the magnetic field from a current in a wire. I draw a wire and I run some current through it. That current is moving charge. And we know that if we have moving charge, that creates magnetic fields. This particular wire will make a magnetic field, B, that's equal to mu naught, which is a constant, times the current in the wire, divided by 2 times pi times r, where r is some distance away from the wire that I'm going to go. So I'm going to create a magnetic field at this point. If I go some distance on the other side of the wire, we'll call this r as well, I'm going to create the same magnetic field. But what's going to change is the direction of that magnetic field. The direction of a magnetic field, the direction of B, comes from a new type of right-hand rule, where I put my thumb in the direction of the current and I curl my fingers in the direction of the magnetic field. We'll show you how this works in class. It's hard to show you here on the virtual blackboard, but the result is that the magnetic field on the right-hand side of this wire goes into the board, and on the left-hand side, it comes out of the board. And I find this is my magnetic field from a long straight wire. And then the next thing that we're going to want to do is figure out what happens if I take a charge and make it move in this magnetic field. So I'm going to take a charge, put it in this magnetic field, and have it moving at some velocity v. Any charge that's moving in a magnetic field is going to experience a force, and we can calculate that. We can calculate that force from the following. The magnetic force from a charge that's moving in a magnetic field is Q times V crossed into B, where this V cross B is a cross product. We should remember cross products from Physics 1. And in general, the magnitude of the cross product is QVB times sine of theta, the angle between V and B. Like I said, this is only the magnitude of the force, QVB sine theta, where theta is an angle between V and B. To find the direction, if we remember for the cross product, we need to use what's called the right-hand rule. So let's say I have a charge that's moving into the page. This charge is moving into this board, into the computer screen that you're watching this from. And there's a magnetic field in this screen that goes to the right. I could use these two directions to figure out the direction of the magnetic force. First, I'm going to point my fingers in the direction of V. Fingers go toward V. And then I'm going to curl my fingers in the direction of B. And finally, my thumb will point towards F. And if I do this, point my fingers in the direction of V, so I point my fingers into the screen, into the board, I curl my fingers in the direction of B, then my thumb will point in the direction of F. And this is what I get. We will do this in class. We'll see an example. You can look at problem-solving techniques on page number 936 to get a little bit of help with this. And like I said, we'll do some examples on the board in class to review this right-hand rule concept. And we can have a situation where we are in a magnetic field and an electric field. In this case, the total force that we have is going to be a combination of forces. It's going to be a combination of the electric force, Fe, plus the magnetic force, Fb. The electric force, we know from previous chapters, is related to the electric field. It's equal to Q times E. And now we can add in the influence of a magnetic force, Q times V times B. And we can get the total force acting on some object that's in an electric field and a magnetic field. So let's take a closer look at these fields that we're talking about, the magnetic field in particular. So if I want to know the units of a magnetic field, how can I find those? Units of a magnetic field are going to be equal to the units of force divided by the units of charge times the units of velocity. This comes from our definition of the magnetic force, F equals Q times V times B. So the units of our magnetic field are going to be newtons divided by coulombs times meters per second. And we give this its own special unit name. We call this a Tesla. And this is the SI unit that we use for magnetic fields. There's also another common unit that we use for magnetic field, something called a Gauss. So these are both two different types of units that you can use to describe the magnetic field. So we know how to find magnetic fields, we know how to calculate them, we know they make magnetic forces, but what do they actually look like? If I want to draw a magnetic field, I need to draw a magnet. Whether we realize it or not, we've seen something that looks very, very similar. We have a north pole on a magnet and a south pole on a magnet. This looks similar to the lab that you did and to some things we discussed in class where we have a charge, maybe a positive charge, and we have a negative charge. We can draw the electric field between these two charges. It goes away from the positive and towards the negative. It goes away from the positive and towards the negative. So we can draw this electric field pretty easily. It goes away from the positive and always towards the negative. And since electric things are very similar to magnetic things, the same kind of field lines kind of apply in drawing the magnetic field lines that we see from a magnet. So we have field lines that go from north into south. So it's a lot like the positive charge that has a field line that goes away from it. The north pole has a field line that goes away. And then the south pole acts like a negative charge and kind of collects all the field lines. So your line goes away from the north pole and into the south pole. Away from the north pole and into the south pole. So magnetic field lines are very, very similar to what we call an electric dipole. They emerge from the north and end on a south pole. It's very, very similar to what we see for this electric field distribution that's called a dipole field. You've drawn it in lab and we've drawn it in class. So very, very similar to electric fields. Since electricity and magnetism have so far shown themselves to be very similar, let's try to make a Gauss's law for magnetic fields. So Gauss's law, the magnetic flux, is going to measure how many magnetic field lines go through a surface. That's going to be equal to the surface integral of the magnetic field B times the area. So to figure out Gauss's law for magnetic field, we're going to draw a magnet. We have a north pole and a south pole. This happens for all magnets. All magnets have a north pole and a south pole. So we can draw a field line. All magnets have a north pole where lines leave from and a south pole where lines enter. I can draw a Gaussian surface around this. And I can count the number of lines that are going out versus the number that are going in. I can see for every line that goes out, for every north pole, there's always going to be a south pole for a magnet. If we remember the very first couple slides, we figured out we can't cut a magnet in half. We can't have just a north pole or just a south pole. There are no magnetic monopoles. So for every north pole, every line that leaves, there's a south pole, a line that comes in. That means that the total flux, the change in the number of lines through a surface, has to be 0. The flux measures the number of lines that leave a surface. And if all surfaces, all magnets have lines that leave and then come right back, then the total flux is 0. So this means Gauss's law for magnetic fields is very easy. The total flux, no matter what, for any magnetic field, for any closed surface magnetic field, is going to be 0. So Gauss's law for magnetic fields, simplest type of problem you could possibly want to do. To get some practice with this, you can check up number 29.2. So to quickly summarize, we know right now that currents, which are just moving charges, produce magnetic fields. Moving charges make magnetism happen. What we're going to do with this is we're going to return to a general definition that we had from the very beginning of a magnetic field of a long straight wire. B is equal to mu naught times I divided by 2 times pi times r. This is the most common way that we move charge around, but it's not always going to be the case. This only works for a long wire. Wires tend to bend. Wires tend to move. So this doesn't work in all cases. We need to generalize this. So we'll take some steps to make this into a more general format. I'm going to multiply both sides of this equation by 2 pi r, try to get rid of my fractions, because as we all know by now, I don't like working with fractions. So I have 2 times pi times r times the magnetic field is equal to mu naught times whatever current I have. If I take a closer look, this 2 pi r is the circumference of a circle. So this is tracing out some kind of circle. What kind of circle is it tracing out? Let's take a look and see if we can figure that out. See if we can visualize what this is actually showing us. So what are we trying to visualize here? We know 2 pi r times b is equal to mu naught times I times a current. So I'm going to draw a current, and we're going to imagine this in a wire, and we're going to imagine this is coming out of the board towards us. So if I use the right-hand rule to figure out the direction of the magnetic field here kind of goes to the left. Over here it's going down. Down here we're going to the right. And the right-hand rule will show us this. We'll see this in class. Magnetic field going up on the right-hand side. So the magnetic field really traces out a circle around this wire. That circle is the magnetic field circumference that we're talking about. Because this distance that we're getting a magnetic field for is r. So 2 pi r, right there, is the circle of the magnetic field, the circle that the magnetic field traces around this current. Now, if the wire is nice and long and straight like this, then the wire is well behaved. But if the wire gets bent, or otherwise distorted, then it's not going to behave this nice little rule, and we have to use something called Ampere's law. Ampere's law will let us get the magnetic field from any current, regardless of the shape. And Ampere's law tells us that the closed path integral of the magnetic field that's parallel, or we can think of it as tangent to a surface, like we have here. The magnetic fields are tangents to that circle, times ds, where ds is how far along this circle we're moving. It's kind of like a little differential piece of radius. So in this case, my ds would be that little red segment right there. I'm tracing out some kind of arc length to refer to terms from Physics 1. So each little piece of arc length along that circle, and that's going to be equal to mu naught times I, the current that's making this magnetic field. So this, I think, Ampere's law, is much more similar to Gauss's law. It's a similar type of approach, similar idea. And in using Ampere's law, you need to make sure that you're integrating around a closed path. That is important. We've been a little fast and loose with closed path integrals, but that's important to note for this. Integrate over a closed surface. And the integrals that we do are a little bit easier for this one than they are for Gauss's law, whether we realize it or not, because we're really integrating over this ds. And this ds, in the case of a circle, is really, really easy. If we go all the way around this circle, integrate all the way around it, we get a circumference of the circle. We get 2 pi r equals the closed integral of ds for a circle. And where it gets weird is when we have different kinds of shapes. If we have a strange shape, a strange path, then we need to integrate across something a little bit differently. To get some examples of that and how that works, look at example number 4 and 5 for practice with Ampere's law. And maybe one of those will appear on your quiz. So we're going to use Ampere's law in a very specific example. In particular, we're going to use Ampere's law to find the magnetic field of a solenoid. And a solenoid is a wire that's coiled. So if I draw a little wire that kind of loops around again and again and again, and I send some current through that wire, the current going like so, going towards the right-hand side. This is an example of a solenoid. The solenoid is just a loop of wire. What I want to do is look at the magnetic field that's created by this solenoid. So I'm going to take this solenoid and I'm going to kind of spin it 90 degrees so that I'm looking at a cross-section of it. So if you can imagine, this is the loop that I'm looking at. If I kind of look from this coil from the side. The current, as I've drawn it, is flowing through this wire, and the current is going counterclockwise. So if I use the right-hand rule for magnetic fields, I can find that the magnetic field in the middle of this solenoid, in the middle of this coil, is going to be coming out of the page. And if I go further, I'll find that the magnetic field outside of this solenoid actually cancels out to 0 because of the influence of these two different coils, two different directions for the current flowing through the coil. They kind of cancel each other out. So this same similar process we can use to figure out that B, in this case, in the case of the direction that this current is going, that the magnetic field through this is going to the right. So we have a magnetic field going to the right for this situation. And it's going to go to the right and fill up all parts of this coil, all the way up to the top edge. So the current inside of this solenoid is setting up a constant magnetic field going to the right. Okay, so now that we know that, we established that, let's figure out how to use Ampere's law to find the actual magnetic field that's created. So what I've drawn here is just a slightly different way, a zoomed in picture of this solenoid. We still have our magnetic field B, and these two dashed lines that I've drawn, these are the edges of the solenoid, the outer edges of the wire. Okay, and I'm going to draw some kind of surface, a Gaussian surface. We can think of it as a Gaussian surface or an Amperian surface if you'd prefer. I'm just going to draw a square. I'm going to draw this square that goes around and has current flowing through it that goes in the counterclockwise direction. And I'm going to say each side of this has a length L. And I'm going to separate it into 4 different parts. I have the first segment, which is going to be this up-down segment. I have the second segment, which is this left to right. I have the down to up segment, number 3, and the right to left segment, number 4. We're going to analyze each one of these segments in terms of Ampere's law. Now I know that I need to integrate around a closed path. B dot ds is going to be equal to mu naught, and I'm going to put in this letter n times I. The important thing here, I is still the current, but n is the number of wires, the number of loops that I have inside of this. We need to remember the current in one loop is going to stack. It's going to increase. And this solenoid, it has multiple loops. So if I looked at a little portion of this to see what it looks like, to see these little current loops, this solenoid is looping around and around and around. And each one of these little loops contributes some amount of current, contributes this I. So I need to stack those up. I need to multiply them together. So I need to multiply my current times n, however many loops are inside of my solenoid. I also need to remember that it's not just any magnetic field that I'm interested in. I'm interested in a magnetic field that's parallel to the direction that my current is going. So what I'm going to do when I'm integrating over this path, I'm going to kind of separate this out into the different segments. We have this integral of B dot ds. It's going to be equal to the integral of the magnetic field in segment 1 dot ds. The magnetic field in segment 1 is perpendicular to the magnetic field that I'm actually inside of. I'm going up and down, and my magnetic field is going left and right. I'm perpendicular, so the parallel segment of that is going to go away. So that's going to be 0 because they're parallel. Then I can add up the next segment, plus the closed surface integral of B parallel in segment 2 dot ds. And this isn't going to go away. This is going in the same direction as my magnetic field. I can add the third segment. Closed integral of B for the third segment. B for the third segment is perpendicular. It's going up and down My magnetic field is going left and right, or in this case just right, so this B dot ds is going to go away. My magnetic field is perpendicular. And then final segment, close the integral for B parallel in path 4 dot ds. Okay, and if we look at this, the magnetic field outside of this solenoid, what is the magnetic field out here? Magnetic field equals 0. We already established that it cancels itself out. So magnetic field is 0 for outside of the solenoid. So this part right here is the only part of interest for figuring out the magnetic field. So I want to integrate across this path, this second little segment, and I need to integrate from a distance 0 all the way to a distance L. If we remember, our little surface that we chose was a length L. So I need to integrate from 0 to L, B dot ds is equal to mu naught times n times I. If I integrate over ds, the B doesn't depend on my position. So I just integrate over ds from 0 to L, and I just get out an L from that integral. So B times L is mu naught times n times I. And I finally find the final answer, the magnetic field of a solenoid is equal to mu naught times n times I divided by L. And what we typically do is we separate this n divided by L and we call it a lowercase n. And this stands for the number of turns in a coil divided by the length. That's how we use Ampere's law to find the magnetic field of a coil. This explanation is to supplement what you read about solenoids in section number 29.4. It's just to make this stuff a little bit more clear, because I don't think this section is as clear as it could be. To get more practice with Ampere's law, you'll want to look at problem-solving techniques, which is going to describe how to do these types of problems, and that's on page 947. And we are going to stop the chapter there. We don't, for the moment, need to worry about the Biot-Savart law. Again, we don't need to worry right now about that section.